It's so awesome actually to see it happening in the lab where we have already proved it in a very small scale. And at the moment, we're building our first lab facility, so scaling it up to the next stage. And it's just awesome. It's just beautiful to see chemistry working in that way. We can't call this a green hydrogen because it's not
Yeah,
only green because we're generating with the electrolysis. No, at the same time, we are doing the carbon removal, so it's a carbon negative hydrogen. So what color is that? So that's why we always say we're just clean hydrogen because it doesn't
that's
really have a
it.
color. So yeah, maybe eventually we'll put a specific color. When you can remove these type of constraints, a lot of things are unlocked. Your techno-economics are unlocked, and then you start seeing also. Then you don't rely on maybe a grid connection, so you can even decrease your CO2 impact a lot more because you don't need to be connected to the grid. You can have your own dedicated renewables without having additional pressure to the grid. Yeah, no, we're very happy about it.
Hey, Aranza, thanks so much for having me today. I really appreciate it.
No, thank you so much for the invitation, Jack. I'm very happy to be.
Why don't we start off with a bit of an introduction to yourself and the work that you do?
Yeah, of course. I have a PhD in chemistry, a little bit more specifically on electrochemistry, that it's working with energy to drive chemical reactions. And a bit further in my background, I have a bachelor in chemical engineering, and I work a little bit all around the place. So I worked for a bit in DuPont as regulatory affairs coordinator for Mexico, Central America, and the Caribbean for the pesticide portfolio. So something completely different. Then I went a little bit into teaching, lecturing topics around engineering and chemistry, etc. And then, of course, I ended up specializing in all things carbon capture. And right now, I am the founder and CTO of Parallel Carbon. And basically, what we're doing is that we're building a direct air capture technology that also produces clean hydrogen. So it allows us to do two things at the same time. So decarbonizing and carbon removal in parallel. So that's a little bit of the idea of the name.
So, I mean, incredible background and career history there. And for you to now focus on decarbonisation and the carbon removal space, sitting across the two, and they're two of the really the most critical areas for our planet today, right? Decarbonising the world that we live in, and then also then trying to almost reverse the damage that we have done through carbon removal. To start off, how do you think about those two different areas at Parallel Carbon?
Well, we see it two like in two cycles and in two processes that integrate each other. And the funny thing is that the decarbonization part, so the hydrogen technology part, it came as a happy byproduct when we tried to understand the direct air capture technology. So basically, the direct air capture technology is this idea of carbon removal, but we take it from the air. As you said, we have done a lot of the damage to the environment. And unfortunately, all of these things that we do keep adding up on the quantity of carbon dioxide that is out there in the atmosphere. And carbon dioxide is the main culprit for global warming. So direct air capture is a technology that allows us to take that CO2 that is already living around us anywhere in the world. So we do it in a one loop. So we take rocks that take that CO2 from the air. These rocks that they take CO2 from the air, we then they have to process them. We do it in a tank with water, with what we call an aqueous process, to take that CO2 from these rocks and be able to put these rocks back to remove CO2 from the air. And then we capture that carbon dioxide gas so it doesn't go back to the atmosphere anymore. So that's one cycle, no? So that's the carbon removal cycle. We're taking the CO2 from the atmosphere. And we want to do it like many times. But in order to be able to do that cycle and in order to achieve this processing that I mentioned to you, we need two very important chemicals. So acids and bases. And these acids and bases, we could go and buy them. They're very known, they're very well studied, the technologies are out there, they're being sold by huge quantities all over the world. But the problem is that the way that these acids and bases are generated is that they have a high carbon footprint, so they also generate a lot of CO2. And in order to make this carbon removal business work, we have to be really negative in terms of the amount of CO2 that we're generating or removing. So we can't just buy things that already have a very high carbon footprint. So in order to balance that out, we realized that if we did a process ourselves to generate ourselves these acids and bases, we can maintain our carbon negativity. And the way of doing it is just using something that is called water electrolysis. That is basically, as I mentioned before, from my background, is just breaking the water molecule using energy. And the great thing is that when you break this water molecule with energy into acids and bases, you're also generating hydrogen. So from this second loop that we have, we're generating hydrogen. That hydrogen is expected to be one of the biggest things to decarbonize industries, because not only it can be used for fertilizers or to power cars or to power houses or to power industries. So it's going to be a really a gas that is going to change the world. So this is how we're incorporating both things. And the great thing is that because these two loops work separately, we can be doing it in parallel. So being doing those both things at the same time, independent of each other. So it's very exciting for us to be doing both things.
Brilliant. I see where the company name came from there.
Yeah, exactly. You
It's
can see all the things.
totally so much to dive into there. Just to start off on the direct air capture side, so the mineral carbonation element that you spoke about right at the start, using those rocks, how does that compare to the other direct air capture companies out there? For example, Climeworks, do they use that same process, or is that something that you differ with?
Yeah, like most of the companies that we're doing direct air capture, in terms of the capture, basically what we're using to take the CO2 from the air, it's very similar. It can change depending on the type of rock, on the type of mineral that we're using, like the chemistry itself. It will be a little bit different. It's all this idea that it's like a sponge. It's a CO2 sponge in the form of a rock. Other companies, other technologies use it with a liquid that has like other chemicals as well that have the same type of process. But yeah, this part of the capture, it's very similar. It's just putting things out there in the atmosphere, arranging it in different ways to accelerate the way that we're taking the CO2. But one of the main differences rely on how we're doing the second part, what we call the regeneration and liberation part. So how are we taking this CO2 from these minerals or these liquids that love to have that CO2 within their chemical structure, and how we can really release that CO2 and be able to trap it, either to put it down the ground or in useful material so it won't go back up there. And that part of the liberation and regeneration has its trick, because these minerals or liquids that are used, as I mentioned before, they really like to have the CO2 within their structure. So you have to be very abrasive and do very strong things in order to take it out. So other type of technologies, like the ones that are within our competitors, the technologies our competitors use, either use high temperature, high pressure, these type of things that will really drive the molecule out of the mineral. So what we're doing is, instead of using these type of systems, because we understand that they use a lot of energy, and unfortunately they're still incompatible with renewables, meaning that because high temperature, high pressure, you can just turn it on and off depending on the availability of this renewable power, the air, the wind, the solar, etc. So because of that, we realized that we needed to do something different. And that's when we found this chemistry that I mentioned before, the acids and bases, that it's also very abrasive in itself and will really help the molecule to release the CO2 so we can trap it. So in terms of the direct air capture, that's our main difference. But it sounds like a small technology change, but the great thing is that it has a lot of impact in the way that these minerals are regenerated. It allows us to have smaller rocks, and smaller rocks means that we can take the CO2 faster from the air. That's one thing. And the second thing is that because we're using this process that it's in water, so it's the way that the chemistry works is like we're doing the mineral like from scratch every time that we're doing it. So that also allows us to have basically no degradation of our minerals. So these rocks can be used in infinite amount of cycles without needing to replenish it with more. So that helps also with the circularity of the process, with the requirement of raw materials, etc.
Sorry, could I pick up on that point around the degradation element?
Yes, of course.
Because what you just described there, saying that there's no degradation, I'm aware that degradation and the cyclical nature of direct air capture technologies or processes is often a bit of a challenge. So having no degradation in your direct air capture process, that could you talk a little bit more about that and how much of a
Yeah, of
win that
course.
is for you?
Yeah, no, completely. That's super exciting for us because, as I mentioned, if you think about anything that goes through very high temperature, very high pressure, these abrasive systems, if you have a rock and you keep doing it and doing it, after a certain amount of time, you're going to be losing a little bit of that material. And that's expected. That's a normal thing because of these type of things. But because in terms of our chemistry, basically what we do is we put in a tank, we put these minerals, we put this concentrated acid. And I know that sounds abrasive, but because it stays in water, you release the CO2 as a gas, and in the water, you maintain like a mineral soup. So these little particles of the rocks are already like part of that soup, so they won't go anywhere. They're just staying there. And then when you add the concentrated base, you make them react again and make themselves appear again, to say it in a way. I know it sounds magical, but that's the great thing about chemistry, that it works like that. That you have this mineral-rich soup, you add this other chemical, and then you're going to obtain these rocks, these particles of these minerals in the bottom of the tank again. They precipitated again. And then you can just take that out and put them back in the cycle. And because they're being regenerated in this aqueous process, in this soup, that's what helps to not have degradation. It's like making them from scratch every time, like making them from zero, from their very basic components, like molecular components every time. And that's why it's super exciting. The main losses that we expect to have is in transportation as we move the minerals. Of course, like an industrial process, we expect to have some losses there, but nothing related to our chemistry. And that's why we think it could be very important in the way that we're cycling, as you mentioned, the cycling of these materials and put them back again. And of course, as usual, because it's a business that we're really interested in that, in the techno-economics of the process.
But I guess just compared to other typical direct air capture processes, I imagine without that limitation on degradation, there's a really high material consumption rate in order to then fuel the direct air capture process. Is that right?
Yeah, exactly. Of course, I don't know the numbers and details from our competitors, but yeah, there's
Mm.
always an amount of material that has to be replenished after a certain amount of cycles. But that implies that you need to consume much more material. And we already understand that in order to remove all the gigatons of CO2 that we need to remove in order to stop climate change, we're going to need a high volume of these materials. So the less we need to replenish in every cycle, the better, because at the end, like we don't get we are not making any extra strain on other systems, on other cycles out there that might be needed for other industrial processes. But yeah, like that's the thing, like that with this type of very abrasive situations, high temperature, high pressure, like after a certain amount of cycles, you really need to replenish them. And as we mentioned, because we're not talking about 1 kilogram of material, we're really talking about tons of minerals.
Mm.
So if we think that the impact that could have in the rest of the environment is something that we have to have in mind. Sustainability is the first thing that we have to consider when we're designing this type of technology.
And just for clarity, the materials that you're using, is it calcium carbonate?
Yes, exactly. It's just calcium
Yeah.
carbonate. So we're using limestone that is highly available. It's everywhere. It's a lot of even waste from the concrete industry. And yeah, that's how we start our process. We start with a calcium carbonate that already has some CO2 in its structure. We do this aqueous processing. We obtain some CO2 that we can capture from that. And then we obtain from this aqueous processing that I mentioned, the acid and the base, we obtain calcium hydroxide, and that is what it becomes our capture sorbent. We remove with calcium hydroxide compared to other companies that they are using calcium oxide.
Brilliant. You mentioned before around the fact that you're not necessarily dependent on the high pressure or the high temperature, which are two typically quite challenging elements to a direct air capture process, in the sense that the process needs either high temperatures and or high pressure in order to be able to fuel it and keep it going. And that's outside of the material consumption element that we just spoke about. How have you got around the dependency for high pressure or temperature?
Well, just playing with the chemistry, to be honest, just trying to understand and analyze what else could be done, like what other ways we could treat these materials in order to make them work. Basically, to take that CO2 from the structure and see what else we could do. And my co-founder Ryan, he's an expert in this type of mineral carbonation and dealing with calcium carbonate. And then he found this idea of using the concentrated acids and the bases, and maybe dealing with some issues with solubility and things that we could get around, and we were able to do it even room temperature and room pressure, which is very exciting for us. And we think that yeah, that's just the approach that we did, just playing with the chemistry, seeing what was out there and seeing what constraints were out there and how we could get around them. It's so awesome actually to see it happening in the lab, where we have already proved it in a very small scale, and at the moment we're building our first lab facility, so scaling it up to the next stage, and even now seeing it in a much bigger beaker to say it in a way. It's just awesome. It's just beautiful to see chemistry working in that way.
I bet, because it really is also, it's such an R&D win to be able to actually remove
Yes.
the high pressure or temperature from the equation. It's one that a
Exactly.
lot of other companies have spent a lot of time trying to get around. I've seen quite a few examples of where the pressure or the temperature has been sourced through sort of other methods, but to remove it from the equation completely is it's incredible. It's super
Yeah,
exciting.
exactly. It's
Yeah.
so good because, yeah, and as I mentioned before, not only that, like when you can remove these type of constraints, a lot of things are unlocked. Your techno-economics are unlocked, and
Mm.
what you can do with that is amazing. And then you start seeing also, then you don't rely on maybe a grid connection, so you can even decrease your CO2 impact a lot more because you don't need to be connected to the grid. You can have your own dedicated renewables without having additional pressure to the grid, without generating all of these conversations that even like the idea of these technologies using a lot of energy has brought to the table. So you can have your own system and operate intermittently depending when the energy is available, etc. So it unlocks so many things when you're playing with the chemistry and you're understanding your chemistry and pushing it a little bit forward and do more than you expect it to do. Yeah, no, we're very happy about it, and we just can't wait to see it in the next scale.
And the speaking about the techno economics, you spoke at the start about the fact that the hydrogen production element was brought into the process to really try and alleviate some of the essentially some of the business case around the direct air capture process, and how hydrogen is almost a happy byproduct of your direct air capture process, which I love. Like that, the sort of phrasing alone, being hydrogen is a happy byproduct, is lovely in
Yeah,
itself. I'm fascinated though. So you spoke about the hydrogen being produced as through the electrolysis process, which is it's the typical method for what we call say like green hydrogen, pink hydrogen, yellow hydrogen, etc. So essentially the renewable forms of hydrogen, also the clean hydrogen. But then that's not just it with your process because it's I'm fascinated by the fact that the hydrogen is produced as a byproduct of carbon removal. So you're not
exactly.
only low hydrogen, which say your yellow hydrogen and green hydrogen claims, but you're almost net negative hydrogen,
Exactly.
which is
Yeah,
incredible, right?
yeah,
I mean,
no, exactly. That's why it's amazing because even when we were at designing and working out our pitch deck or even our value proposition, a lot of these things is
yeah,
yeah, we can't call this a green hydrogen because it's not
yeah,
only green because we're generating with the electrolysis. No, at the same time we are doing the carbon removal, so it's a carbon negative hydrogen. So what color is that? So that's why we always say we just clean hydrogen because it doesn't
that's
really have a
it.
color. So yeah, maybe eventually we'll put a specific color. Unfortunately, our branding is all based in green, so it couldn't be
Maybe.
like
I
parallel
mean,
green,
because
but we'll see.
yeah, because we've got the spectrum, we've got the sort of color spectrum of hydrogens going
Yeah,
from like the black hydrogen, but then everyone sees the end of the spectrum as being green hydrogen. And then
exactly.
you've added a step.
Yeah,
You've added a
exactly.
step.
Yeah,
It's
no, which is amazing for us. Yeah, and the moment that we realize the potential that it could be, because to be honest, at the beginning we were just seeing it as, oh yeah, we're getting hydrogen, or maybe we can reuse it with a fuel cell, so we decrease our
yeah,
energy consumption, and it was like, yeah, it's part of it. But when we realize the power that it really has, and of course the opportunity that it means to have the hydrogen, and as you mentioned, this idea to be able to provide a carbon negative hydrogen and the impact that it has, and not only in the fact of how you're using the hydrogen, but also when you start to understand the techno-economics of our own technology. My co-founder Ryan, he's a master of all of those type of things, techno-economics, and he has been able to do some very amazing models to try to see the impact of us selling this hydrogen or providing this hydrogen. And the amazing thing is that because how we're generating it, it's basically the electrolyzer paying for itself by selling this negative hydrogen because it's
mhm.
this happy byproduct. Because we won't really be using it ourselves, and it could be provided to an industry that requires decarbonization in their own raw materials, for example, the fertilizer industry or something like that. So it unlocks so many things in so many different levels. And we hope that it could be a beginning also for another type of industry, maybe unlocking demands of other scientists and think what other ways hydrogen can be produced, not only from the electrolyzer, but other technologies that can have it as a, that maybe now it's a happy byproduct and they haven't realized.
It goes without saying that the opportunity for your hydrogen is as broad as the hydrogen market as we know. So you could put it into vehicles, you could put it into fertilizer, as you say, you could use it for a long list of different types of applications. So I'm assuming that full market spectrum is open to yourselves. And maybe actually the type of hydrogen that you are able to provide is almost more attractive than other types of hydrogen because of that net negative carbon footprint associated with it.
Yeah, of course, the potential is enormous, especially now that the hydrogen market is expected to be unlocked in so many ways, and not only we're not only talking about the UK or Europe or the US, like around the world is something that we expect it to be something that it could become more widely available in so many things. At the moment, we're expecting it to be more used as a chemical feedstock more than anything. So hydrogen that is used to produce chemicals right now is what we're seeing, like where our hydrogen or our opportunity can be locked into place, especially because the whole sector around transportation and vehicles and hydrogen use as a fuel source for energy is still something that needs to be explored a little bit more. Although there are a lot of advancements, and for example, we have a big project here in the UK called HyNet that is expected to be able to deliver hydrogen for many uses. But we believe that at the moment, especially for the scale that we will be working at in the next couple of years, the idea of providing it to a fertilizer producer is what makes a little bit more sense. But yeah, well, but as you mentioned, like the potential is endless, and our main constraint at the moment, I would say, is this the availability of hydrogen off takers, because funny enough, it's something that it's in the mind of a lot of people because a lot of the technology has not been developed yet to be used in all of these applications. And of course, regulations are still being developed. Regulations is something that still need to be a lot of decisions around them. So we'll see, and even for us to define even the color of this hydrogen, see how we're gonna put it properly in the market to differentiate it against the others.
So the big sort of gold standard, as we know, for direct air capture is to getting the cost down to $100 per ton of CO2 removed. There are lots of different research papers that suggest that is really the threshold that we need to get to. World Economic Forum, for example, uses that figure. I think they state you have to get to $100 per ton of CO2 by 2050 or something to be able to really have the scale of impact and benefit that we need. In terms of the business case for yourselves, because of that hydrogen element almost making it more economically viable, are you able to actually then produce a more advantageous carbon ton removal figure?
Yeah, of course, because at the end, our entire technology, our entire like the idea of the carbon removal, that because it's ingrained in both cycles that I mentioned. As I mentioned before, having this hydrogen and with the idea that we can sell it and obtain profit from that compared to other dark companies that basically the revenue is directed only on the CO2 gas and the carbon credits that they can manage to sell, because we have this hydrogen byproduct, this hydrogen gas. We can also sell it, and the revenue that is coming from that basically pays this part of the electrolyzer that is producing the acids and bases. So at the end, we can really show or reflect this profit that we're obtaining from the hydrogen into the entire economics of the system. So the capex of the electrolyzer is already covered by the revenue from the hydrogen, and that really helps us unlock a lot of our things on the techno-economics and really decrease our price considerably. And yeah, like I try to reach this magic number of the $100 per ton, and our idea is to reach it by 2030. Our plans and the milestones and what we have projected is that we will be able to achieve it by then. And of course, hopefully by 2050, even achieving lower prices, of course, benefiting the entire industry. So yeah, no, having this additional thing completely unlocks so many things for us.
What sort of hurdles do you see being in your way to sort of reaching that utopia here?
Oh, yeah, that's a great question. Because I'm going to speak from our scale to scale up. No, of course, that's the first big hurdle. Taking this idea that has been working beautifully at a lab scale to actually something that works like a proper industrial scale. So that's what we're working at the moment, and we're looking into that. And one of the great things about that is that we're surrounding ourselves with the best partners to be able to try to foresee all the potential engineering hurdles and problems that we might have through the scale up. So that's the first one. No, of course, this idea of taking something from the lab scale to an industrial scale is the first hurdle. But of course, for technologies like ours, and for direct air capture in general, one of the main things is like where you locate. Where are you going to put this plant? At first, it requires a considerable size of land in order to be located and to distribute all the things that you need. But also, you need to know what you're going to do with the CO2. And in our case, it's what are we going to do with the hydrogen as well? What are we going to do with both gases? Because of course, in order to maintain your cost low and your operability high and the things that you want to achieve, ideally you don't have to compress these gases, you don't have to transport them for long. So the best scenario for us would be to be located somewhere where we would have both off takers on the same site. And that's when like these fertilizer producers or SAF, maybe like sustainable aviation fuels, could be interesting, etc. So that's another thing. Now, what we're gonna do with the gases, but that it's interesting. Last week we were in a hydrogen conference, and one of the main things that everybody mentioned, it was like the necessity of developing these off-takers, like who is going to be using the hydrogen for energy? Because of course we all know who uses them for chemical feedstock and stuff, but also we can produce tons and tons of hydrogen, but then who's going to be using them? No, so that hurdle of going back, like to develop these other technologies at the same rate that we're developing these ones, so they can be utilized. And then on the side of CO2, at first on a small scale, we want to provide it to someone that is doing building materials, so concrete or aggregates, so they can have the CO2 permanently ingrained in those building materials. But when we start capturing a lot more, we'll probably need to inject it underground. And in order to do so, you need the right site, you need the right permits, and of course you need the right permits and at the right time. So you need to accelerate the permits. So we're going back to regulatory perspective. So these regulations be in place so we can start doing all of these. And last but not least is, of course, the always having in mind the environmental justice and how we're going to set this up, how we're going to educate the public around, how we're going to educate our new employees and everybody to understand what we're doing and why we're doing it and how we're doing it. You know? So that's a very important thing. That even though I think that's being developed quite well in the US and in the UK, but there's still a lot of things that need to be done in order for us to be able to achieve this utopia, this carbon removal utopia. And last but not least, of course, the money, how these big projects are going to be funded. Because not only on the carbon removal space, but also on the hydrogen, there's this big question of when we start to scale up and all of these companies start moving, the companies that can reach to that stage start developing and having these big projects that require a lot of capex and a lot of money upfront in order to be able to do it. So where the money is going to come from? Is it going to come from project financing? Is it going to come from investors? Is it going to come from oil and gas? What are the implications, etc.? So I think that's a huge thing that needs to be understood in terms of the entire carbon removal market. But I think that at least for now, we're in a very exciting time because everybody has a lot of ideas. Everybody has a lot of opportunities and potential, and a lot of companies and a lot of stakeholders are trying to understand and really understanding that we need to do this now, that we need to start moving now, because if not, we're not going to reach any target by 2030.
Quite a few different points there that I would love to dive into, but maybe just going back to one of the previous ones around almost moving it around essentially. So you spoke before about the work that you do in parallel carbon, you've now essentially got the hydrogen generation capability pinned down. So that is known, the economics are known. Projects like HyNet allow us to then move that hydrogen around. We've then got equivalents for CO2, so be able to move CO2 around through pipelines around the UK. And then on the, I guess, consumption element, you spoke before about the sort of general consensus in the industry around the level of developments that has gone into being able to use these materials in existing industrial processes. Do you think we've been too ambitious in the generation and not necessarily had our eyes on the prize in terms of actually being able to make the use of it? Or do you think that we've been able to make more progress than we were able to ever imagine in the generation of clean hydrogen?
I think that we have done a great job and we're on the right track. But I definitely think that there's a lot more that needs to be done in the off-taker side. Who is going to be using this hydrogen and how are they going to be using efficiently? Because at the moment, like even though we know that fuel cells are out there, fuel cells can be used, unfortunately, their efficiency, how they operate is not the best yet. I think that there's a lot of things that need to be there in order for them to be used in much higher volumes. And I think that's why a lot of these projects that rely as hydrogen as a source of energy have not really moved forward, because hydrogen as a source of energy still needs to be implemented in many different ways. And maybe in the way that we have been explorer electrolyzers for so long, I think that we need to have a lot more effort on understanding fuel cells in the same way, so we can really use the hydrogen properly and explore it in different ways. And also that's why hydrogen vehicles and all of these things in a smaller scale have not been explored a little bit more. And in that way, for example, I've seen, like in the conference that I was mentioning that we were participating last week, I saw a lot more discussion around airports and ports and bigger applications. But once again, then you have to start thinking about boats that use hydrogen and SAFs and how it's going to be working in an airport and the safety and everything. So there's a lot of things that need to be done over there. And I think that there's definitely more resources that need to be invested there.
Yeah, it's interesting to think about because we've heard about hydrogen powered X for quite a few years now. Um, I think I think I seem to remember London buses being hydrogen powered years and years
Yeah.
ago. But it's interesting to think the journey of iteration that it's been on and seemingly has still quite a way to go. It's interesting to think about the different types of sectors and applications that the sector is going through. We, as I mentioned before, we saw it at a consumer level, so hydrogen powered homes. You gave the example there of ships, airports. It seems to orientate around the transport area. It's interesting. I wonder what the final application will end up as.
Yeah, no, I completely agree. And because it's so unclear at the moment because there's so many ideas and so many possibilities put out there. But I think that there's also like this fact that it needs to be understood. Like this, of course, generating this hydrogen and obtaining this hydrogen is still it's an energy intensive process. So it requires a lot of energy in order to be produced. In order like to have that energy, ideally it has to be clean energy, and we still don't have enough resources as well in terms of clean energy, or it is still not decarbonized. So it's something that it still needs to be explored as well, because it doesn't matter if you're generating this very clean hydrogen that is being used to power all of these things, if this hydrogen is still being produced by a grid that is powered by oil and gas. No, if you still don't have this chain or this line complete to on how it's every asset is decarbonized, at the end you're covering one hole with another one. So it's something that we still need to understand as well and explore a little bit more when we're thinking about producing these things. And of course, in the UK we can talk about offshore wind and the potential of solar power, but will this be enough to have all of these assets decarbonized? So it's something that we still also have to have on the table and discuss it a little bit more.
Aranza, thank you so much for joining me today. I really appreciate it. It's been absolutely fascinating.
No, thank you so much for the invitation, Jackie. It was a pleasure, and I hope I see you again soon.
Thank you.